So everything we've been talking about is looking at the case where we're aiming to find a single point estimate theta hat, which has been the MLE, maximum likelihood estimate so far. Now, something I mentioned earlier, a limitation of this approach is that once we do this, once we pick a point estimate for theta, we lose any uncertainty about what that theta was. And there are a lot of cases where this can be a problem. So a very simple one is, what if we're doing MLE estimation of what is the MLE estimation for a Bernoulli distribution? That is, let's say we flip a coin, we get 3 heads, and we want to know what is the proportion of heads that that coin gives. And if we did MLE, using that expression we showed earlier when we did MLE for a Bernoulli distribution, we would get that our theta hat is 3 divided by 3 plus 0 equals 1. And likewise, the probability of tails is 0. Now, maybe that's okay. Maybe we think that's an okay estimate. After all, we haven't seen any tails. But especially in the case where we're dealing with like a physical coin, we definitely have some prior knowledge that there's probably some way for that coin to end up landing tails. It's probably not impossible. Which is to say that this estimate is probably too confident. We probably want to give some like slightly less confident answer for what we're going to see in the future. We probably don't want to say that there's a probability 0 of seeing tails in the future. Now, again, one way to handle this would be to use our posterior distribution over theta. If we did that, we would get something like this. If here's our theta and here's the probability, that is, it puts high probability on theta being equal to 1, but there's a lot of probability that theta is less than 1. And if we were to be kind of a fully Bayesian, and we wanted to predict what coin flip values, heads or tails, we see in the future, we would use our posterior predictive distribution, which is we sum up for all the possible values of theta for a future flip weighted by the posterior probability of that theta, and that would be our prediction for what future flips would be. But let's get out of that case, because often in real cases that's computationally infeasible to deal with this full posterior distribution. And let's look at the case where we want a point estimate for theta hat. How can we overcome this issue of overfitting, where theta has kind of overfit to the fact that we saw in just our very limited training examples of 3 head flips that we saw just 3 heads and no tails. A very powerful tool in this case is to add a prior. So that is, let's switch to, instead of asking for the maximum likelihood estimate, let's ask for the map estimate, that is the maximum posteriori. So let's look what happens when we do that. We want argmax with respect to theta of the posterior distribution instead of the likelihood probability of theta given d. That equals this expression here, where we use Bayes' rule, that is probability of d given theta, the likelihood, times the prior, divided by the probability of the data. Now, notice a few things. First thing, notice that probability of data is constant with respect to theta. So this term goes away. Also, we're going to do the same thing we did for likelihood, where we take the log. Once we do that, this expression becomes the following. This first term, where this is the likelihood, I've written it out again in the IID form where you have the sum over our different examples, then plus the log of the prior. So now notice that this looks almost identical to finding the MLE. We still have that same term here. This thing is exactly equal to the log likelihood that we optimize when we're looking for the MLE. But then we have this other thing, which is the influence of the prior. So in this form, we can use the prior to encourage some features or to express our prior knowledge about what theta should be. So for example, in the case of the coin, we might think it's very unlikely for theta to be a extreme value that is close to 0 or 1, so we could define our prior accordingly. And then once we optimize this combined thing, the prior plus the likelihood, we'd get some value for theta as our map estimate that's that perhaps is more preferable, works better if we apply in the future. Okay, now let's compare map estimation to another concept, which you'll see often in kind of non-probabilistic machine learning of regularization. So if we use regularization for an empirical risk minimization problem, what does that look like? It looks like this. We minimize, here's our normal empirical risk term, where it's the sum of our loss function. Then we add this term, which is our regularization term. That is, it is some other loss function, which notice depends just on theta, which again expresses some preference we have about theta. So for example, we might put a very large negative value on values of theta we don't like. For example, in the coin flipping problem, for values of theta close to 0 or 1. And then when regularization is used, we often use this this factor of lambda to control the strength of regularization. Okay, so now that we just saw map estimation on the last slide, let's go back there. Notice that that looks almost exactly the same. This first term we saw before is our log likelihood term, which is just a special case of the empirical risk term, where we're using the log likelihood as our loss function. And then we have this additional term, which again depends just on theta, which is our prior. This could be, this again is this you can think of as a special case of regularization, where we're using a log prior as our regularization function. Okay, let's do an example of map estimation. So we're going to go back to the Bernoulli distribution. And to do map estimation, notice that we need to define a prior. So let's define our prior. We're going to use, in this case, a prior as a beta distribution. We haven't defined a beta distribution yet, so let's do that. This is defined in the book back in chapter 3 in a part of the book that we skipped. So the beta distribution is defined like this. It takes its output as a parameter, which for us will be theta. We're using x here in the definition, and the value is like this. This thing is a constant factor, which is defined in the textbook. I'm not going to write it out here, but it's some constant factor that depends on a and b, and then the density is x to the a minus 1 times 1 minus x to the b minus 1. So if you look at what this looks like, if here is, I'm going to draw theta since that's the output, and here is the probability. Let's use a equals b equals 2 here. The density is going to look something like this. It's going to be between 0 and 1, and it's going to be highest in the middle. Okay, so let's see what happens when we use that as our prior distribution. So let's write out our log likelihood, or actually, in this case, our posterior, our log posterior. So again, this is just our log likelihood, this first term here, plus our log posterior. Again, we got rid of our normalization constant, log p of d, because we're just trying to optimize with respect to theta. So that's constant with respect to theta, so we don't need to include it in our optimization. So this is our first term here. That's our likelihood term. Here's our prior term. This one we've seen before. Again, n1 and n0 are our number of heads and tails respectively. And then this thing here is just the log of this thing here. Again, I've thrown away the constant factor because it doesn't depend, it won't influence our optimization. So notice that there's this nice symmetry, and in fact, this is why we picked a beta distribution. Notice we have n1 times log theta here, and here we have a minus 1 times log of theta, so both with log of theta, and then here b minus 1 times log 1 minus theta. So that means that once we take the derivative and set it equal to 0, we get something that looks like this. Our optimal theta, the maximum this thing, I'm not going to do the algebra here, but it's pretty easy, ends up being this. n1 plus a minus 1 divided by n1 plus n0 plus a plus b minus 2. So if you look at this, you realize this is exactly the same as if we had observed a minus 1 and b minus 1 additional heads and tails respectively. So this is kind of a way, adding this prior is what it does functionally is kind of add pseudo counts to our data. That is, we pretend like we already saw one head and one tails before we start observing our actual data. And in the case of where we see 3 heads and we're using a and b equals to 2, that's going to give us 3/4 rather than, or 4/5 rather than 1. So this has solved that issue that we had before, where we were getting 1 as the output of our estimation.